All right, so what we are going to do today is take a look at these three noded quadratic finite elements. Um, so this is something like more generalized version of the finite elements that we took a look at before. Um, so what we were doing before was this linear polynomial approximation with a two-node finite element. So we said that we could approximate our solution, the exact solution within one element. We could approximate that with this sort of expansion, where we said that these, I think there's something, these things get shifted on my computer, I don't know why. Um, so Right. So we said that this n matrix is called the shape function matrix, and it just is composed of all these shape functions. In general, there will be more shape functions, but there, in this case, there are only two shape functions. So these are the nodal degrees of freedom, which just means that how much does this node 1 displace and how much does this 2 node displace. So those are the nodal degrees of freedom. That will give us our approximation. Similarly, you can approximate the virtual displacements with the same shape functions. And there's a bar for the virtual displacement. And finally, we also said that if you wanted to calculate the strains, the real strains within the element at any point, that could be also calculated using the derivatives of the shape function matrix, which we are denoting by B. So if you use all that, then we found that the stiffness matrix for each element was going to be given by this form, the derivatives transpose times some. In general, it will be a matrix, but right now it's a one-dimensional scalar. So B transpose C B, and the element force vector was going to be a 2 cross 1 force vector, which is also given below. So in the very special case, let's say if the material properties within the element are constant, and let's also say that the body force is constant. In that case, you can actually explicitly integrate this expression. So if you write this out as a column vector, write this B out as a row vector, you can explicitly multiply this out and find this. And actually, this is something that you could have directly coded up in your element stiffness matrix for the homework 3 that I assigned. And also in the special case, when B is constant, so in your homeworks, B was not constant. So you couldn't have done this. But in general, if B, the body force, is constant within the element, then you can also express the body force or the force vector as B times LE, which is the total force, right? So if you look at one element and the body force is constant within that element, then the total force that this element is going to be feeling is going to be the body force times its length. And if there is an area of cross section, you can also include an A in here. But essentially what you're doing is you'd be integrating the shape functions over the length of the element. And that just means that half the body force goes to this node and half the body force goes to this node. This is also something that should be familiar from structural analysis. This is where it comes from, the half and half dividing onto the two nodes. So once you have these element stiffness matrices, you can just go on and assemble them, and assembly was just adding the terms in the correct degrees of freedom. Okay, so if you assemble them, and you can finally add on any extra nodal loads, and you would be solving this equation, this parenthesis equation in the middle, to be equal to 0. So that was what we did before using two-node linear finite elements. So today what we're going to try to see is how to develop higher order polynomial shape functions when you can include an extra node within the element. So let's say this is our element E. starting from this node all the way up to this node. And we are going to add, for the time being, just one node in the middle, which gives us a total of 3 degrees of freedom per element. Okay, so since we have 3 degrees of freedom per element, we can approximate all the way up to uh, quadratic solutions within the element. So one way to generate these shape functions is called the Lagrange interpolating polynomials. And let's take a look at what would be the first polynomial. So we know that we want our first function to be 1 at node 1. So our first shape function should be 1 at node 1, and it should be 0 at the 2 other nodes. So to generate that, what we will try to write this as, let's say, n within the element node 1. That shape function is going to be a function of x, and it's going to be written out as x minus xe over 2 divided multiplied by x minus xe3. So if you try to calculate this shape function at, let's say, node 2, you plug in the value of x. X at this point would be xe2. This is the node value of that node. So this term goes to 0. So obviously this shape function would be 0 at node 2. Similarly, if you plug in the value of x as x element 3, this node, then this term goes to 0. So we now know that this is a quadratic shape function, and it is going to go to 0 at this point and at this point. But how do we make sure that it goes to 1 at this point? Any idea? Okay, yeah. So if we divide this by xe1 minus xe2 and xe1 minus xe2. So now if you plug in the value of this node, if you plug in the value of x as this node, you see that this will go here and this will go here. Both the terms in the numerator and denominator cancel off, and we get 1. So if you were to plot this function, that would look something like this. And let's see. So this is what it would look like. This part is not linear. It just turns out that I've drawn it that way. So similarly, you can write out the other two shape functions. The other two shape functions are going to be at node 2. We are going to write this as x minus xe1. And so this node should, this shape function should go to 0 at node 1 and at node 3. So if you divide this out by 2 minus xe1, that's the first term, and xe2 minus xe3. So once again, this shape function will go to 0 at nodes 1 and 3, and it will go to 1 at the node 1 at node 2. So what this might look like is something like this. And finally, we have the shape function 3. Just according to the same concept, x minus xe1, it should go to 0 here, and x minus xe2, it should go to 0 here. The whole thing divided by xe3 minus xe1, x element node 3 minus x element node 2. So this shape function would look like this. And all these values are 1. Okay. So these are in general called Lagrange shape functions or Lagrange interpolation functions, and you can generate any number of these shape functions by including more and more nodes within your element. So this is the shape function that we are going to choose. One important point, I guess, here to make is that uh, this node need not be in the center of these two nodes. You can place this node anywhere. Um, Later on, we'll see that there are actually some restrictions on where you can place this node if you are using numerical integration. But for now, we'll say that we can place this node anywhere in the middle. But in general, if you actually place it right at the half point of these two, then that gives you better results in finite elements. So let's choose these shape functions, and using these shape functions, we are going to try to solve uh, a one-dimensional problem. So in this case, what does this n matrix look like? We say that the the real displacement, the solution within an element is going to be approximated by this same shape function matrix times degrees of freedom within the element. And what this would look like is NE1, NE2, and NE3 times the actual degrees of freedom within the element, DE1, 2, and 3. So similarly, you can also approximate the virtual displacement and the real strains. So if you notice that this kind of a notation that we also were using for the two-dimensional finite elements is equally valid for in this case also. And this is going to be a standard notation for 2 dimensions, 3 dimensions also. It's just that the structure of this shape function matrix and the degrees of freedom within the element is going to change. Okay, so now that we have approximated this displacement and the virtual displacement and strains in our case, we can go back and plug it into our weak form. So the structure of the weak form also does not change. We were saying that the weak form is going to be the sum over elements of this quantity. So this quantity is the same way. It doesn't depend upon the number of nodes in the element. So this is the same type of quantity that we also were using in the two-node linear finite elements. And then we also have the same type of thing that we could have nodal forces acting at the nodes. So here again, I'm just showing you that the boundary value problem that we are trying to solve could have m total elements. In this case, I've just shown 3 elements. And I've labeled the middle nodes with a blue color just to demarcate them, and I'll tell you why this is important. So, so then this is the stiffness matrix for the element. This is the exact same formula that we had before. And this B, what is the size of this B going to be? B transpose. So if my shape function matrix is 3 cross 1, the derivative matrix is also going to be 3 cross 1, and B transpose, the derivative transpose is going to be, sorry, this is 1 cross 3, so this would be 3 cross 1. And 3 cross 1 multiplied by a 1 cross 3, that means that each element stiffness matrix is going to be a 3 cross 3 in this case. Okay? So all that we need to do now is to try to assemble them. And here is a little different thing about these 3 noded elements. What you could do in this case also is go about the assembly process exactly the same way. So if you assemble the equations, you have this equation or this contribution from the first element. You have this contribution for the second element, and so on. But note that in order to be able to add these things up, what we are saying is that the degree of freedom 3 from element 1 is actually the same as degree of freedom 1 from element 2. So this is the assembly process that you should have all actually used even for your one-dimensional finite elements, right? So you can go about the same way, assemble all the 3x3 matrices to form one big stiffness matrix. But the tricky thing about, or not, there's a better way to do that. And the reason that we want to do it in a different way is because if you assemble all of these equations, what that would do is it would increase the size of your total global degrees of freedom. Okay, so let's consider this case. If I had 3 elements and 2 degrees of freedom per node, like we were doing before, the linear elements, how many total degrees of freedom do I have? If I have 2 nodes per element and 3 elements. So 3 elements means total 4 nodes, 4 multiplied by, so that's 4 degrees of freedom, right? In this case, since each element has actually 3 nodes, then 3 elements, the total number of nodes is going to be 1, 2, 3, 4, 5, 6, 7. So I've just increased the size of my stiffness matrix to a 7 cross 7 instead from a 4 cross 4. And in general, that is also going to be true for higher dimensions also. But and you can imagine that if you have a finite element mesh that is maybe thousands or millions of degrees of freedom, then a 50% increase in the size of your stiffness matrix is not going to be good. So in this particular case, there is a very neat way of rearranging our equations such that we end up with the same size of global stiffness matrix that we had before. And so let's take a look at this. We know that these degrees of freedom from the neighboring elements are the same. But how about this degree of freedom? So this is the degree of freedom 2, which corresponds to the middle shape function, which is this shape function right here. And it's not connected to the rest of the mesh by anything. It is completely independent. Does that sound correct? If you take a look at this degree of freedom, the first element, degree of freedom 2, this is not connected to the rest of the mesh because its value at the 2 ends of the node of this element goes to 0. So this is actually just an independent parameter, independent coefficient. So last time, or when we were talking about these 2 node finite elements, I told you that you have to sum up all these equations and then you can set the thing, the total equation to be equal to 0. But if you look in the book by Reddy, or actually there are quite a few other books also, they do tend to make this error that individually all these equations are set to 0. That's not correct. You have to assemble the equations before you can set them equal to 0. So equilibrium does not hold for individual element equations, but only for this bubble shape function. Because this looks like a bubble, that's why we call these kinds of shape functions bubble shape functions. Okay. So only for these bubble shape functions, we can see that they are not connected to anything outside this element. Therefore, we can actually collect the equations, this second equation right here. So if you collect this equation, and if you collect this equation, and similarly the second equation of every element, if you collect them out, those equations actually do hold. So this equality holds for these special bubble shape functions. So let me go through this. If you pick out the second row of this element contribution, what do we get? This is the second row times this vector. So second row times this vector is actually equal to the right hand side. Okay, so this equation holds for bubble shape functions. And now if I try to calculate this degree of freedom 2 in terms of the other 2 degrees of freedom 1 and 3, then I can use something called static condensation. All I'm doing is taking the stiffness and the equation corresponding to this bubble shape function and expressing the solution of that in terms of the other two shape functions I had. Okay, so how many of you have heard actually of the static condensation before? Okay, um, so this is the same sort of concept. Um, so what we are saying is that we are going to write this equation out in this form. So all I'm doing is taking this middle stiffness term times this, which is on the left hand side. On the right hand side I have Fe2 and minus this plus this multiplied by this. Okay, so this is just a rearrangement of this equation. And the reason that this is going to help us is because now I can take this quantity, inverse it, and switch it to the right hand side. So if I do that, what I will get is this inverse times all this. Okay. So what I've been able to do now is to express this degree of freedom, the bubble shape degree of freedom, in terms of the other 2 degrees of freedom. The other 2 degrees of freedom were actually connected to the rest of the mesh. Okay, so we cannot eliminate those two by static condensation. So so in general, what you can also do is, so in this case, what we had was just one bubble shape function. In general, you could have 2 bubbles or 3 bubbles or as many higher order shape functions as you want. So if you have multiple bubble functions, then you can actually again partition your stiffness matrix into this form. Let's call this main mesh, and this is bubble degrees of freedom. So I'm removing, or I'm collecting the main mesh degrees of freedom at one place and the bubble degrees of freedom in one place. And I can write out the element contribution from this element in this form. So all I've done is exactly this equation, or this contribution for a general element which has some m degrees of main degrees of freedom and b as the bubble degrees of freedom. Okay, and exact same formula that you have here, we can express the bubble degrees of freedom in terms of the main degrees of freedom. So all I'm going to do now is to take this formula or this formula and plug it back in into each of these element equations. So if I do that, what we get is this part in your handouts or it's not? So yeah, I'll post this anyway, but if you can, try to take notes. So what I'm going to do is I'm going to just substitute DE2 into my original equations. So for example, here, if I eliminate the second row and the second column, what I will be left with is these 2 cross 2 submatrix, right? And what I can do now is that submatrix is right here. So I'm only writing it out in terms of the main degrees of freedom. And now I will also write out this K12 times dm2. Do you see that? Let me actually write that out then. So well, actually it's written here, so let me not do that. Okay. So this was the submatrix that I was just telling you about. We are picking out these 4 elements. These are these 4 elements, and these degrees of freedom are right here and here. But if you consider the first row and the third row, there is this contribution also sitting in here. So K12 and is there something wrong in here? Okay. Yeah, there's a couple of indices mislabeled here. So this should be K1, 2, and this should be K3, 2. And these indices should also be K21 and K23. So this was, all I'm doing is collecting this term and this term multiplied with this. So that's right here. K22 inverse times K21 and K23 times the main mesh degrees of freedom. Okay? And all I need to do now is to take that, multiply it with KE12, that's right here, and KE32, that's right here. So this is a 2 cross 1 multiplied with a 1 cross 2. This will also give you a 2 cross 2, right? In the middle here, it's just a scalar in this case because we have only one shape, one bubble shape function. But if you have 2 or 3, then again this would just be a matrix, and you would still get 2 cross 2. So this is just a little bit of a rearrangement of equations. This is a very interesting process. If you actually, you might have heard of enriched finite elements. So people try to add these kinds of bubbles, and just so that the cost of the total solution does not increase, you can eliminate those local degrees of freedom using this static condensation. So in general, if you have multiple bubbles, what you can do is write out this element contribution into this form. So this is KMM right here times DE, that's right here, and I'm going to take that DE out common, and what I'm left with here goes into this. So this is KMB times K bubble inverse times KBN. So this is nothing but just a partitioning of our element stiffness matrix and just a little bit of a rearrangement. Once you do that, you can also do the same sort of a rearrangement for your right hand side. And the new element contribution becomes this. Okay, so what we have done with this element contribution is that we have eliminated all the degrees of freedom that were corresponding to that bubble from our global weak form. So here's a couple of other terminologies also. This term right here, this is called the Schur complement. The Schur complement of the bubble shape functions. And this is the contribution in general. If you do a static condensation for some degrees of freedom, this is the kind of contribution that you will always get. You will get some K transpose times inverse times a connectivity matrix. So when you assemble all these equations, now you can go back and assemble them into your global stiffness matrix, and that assembly process will be exactly the same as what you had before for the two nodes. Does that, are you able to see that? Now that I have reduced my element contribution to a 2 cross 2, I can go back in our global degrees of freedom. I can eliminate the second row, all these second degrees of freedom from these elements. The second degrees of freedom here, I can delete this second row and the second column, and instead I will replace it with something that I'm calling an effective element stiffness matrix. Okay, so this was the stiffness matrix corresponding to the main degrees of freedom that we had before. If I subtract out, or if I add the Schur complement of the bubble, then I will get the effective stiffness matrix for the element. All right, so let me ask you a question. If I have, let's say, one element, I started with a 2 node, Now I added, let's say, 3 bubble shape functions in the middle. So there's a total of 5 nodes per element. Okay. So what would be the size of the element stiffness matrix without static condensation? 5 cross 5, right? So, and now if I do the static condensation, what is the size of the reduced or the effective stiffness matrix? 2 cross 2. So I have reduced the size of my stiffness matrix by an order of magnitude in general if I have higher shape functions. So now if you assemble all of them before, just like before, you will get this equation. This is something that we also got for the 2-node element. And all I'm doing is denoting it with a super tilde to, to, to show that this is actually an effective stiffness matrix. Okay? Was there any question? So once you have this, you can actually just solve for the main mesh degrees of freedom. And that would actually mean that you would solve for this, which is fixed. So you again you will solve you will enforce this boundary condition just the same way that we divide it into 2 parts, specified and free, and so on. So ultimately, what you would be solving for is this degree of freedom, this degree of freedom, this degree of freedom, and this degree of freedom. And once you solve for those main m, let me label them. These are the m degrees of freedom, and these are the bubble degrees of freedom. So once you solve for your main degrees of freedom, you can go back and calculate your bubble degrees of freedom from this equation right here. So you can go back within each element and you can find out what this is. Also, another thing to note here is that this sort of a procedure would be helpful only if you can calculate this quantity easily. So this is the bubble degrees of freedom, the stiffness matrix corresponding to the bubble degrees of freedom, and we are actually explicitly inverting it. Okay, so this process can be sometimes expensive, but if the bubble shape functions are actually orthogonal, then most of the time people choose those shape functions to be orthogonal so that this KBB is actually diagonal. And if it's diagonal, the inverse is just the inverse of each diagonal entry. So this quantity gets calculated very quickly. So you can see that you can actually add nodes in your one-dimensional finite elements to get a much more accurate solution without at minimal cost, right? So all you are doing here is all these calculations were within one element. So those calculations go very fast. This is the main calculation that you are doing for the entire mesh, and this is the exact same size as we had before. So you have not really increased the computational cost of this thing. So so this is basically how you should be implementing a 3-node finite element. But in your book by Reddy, they do not discuss this procedure. So in general, if you have higher order shape functions, you can still go ahead and assemble all of these equations as before without actually benefiting from this. But if you want to save computational time and if you want to write an efficient program, then you should try to find these kinds of efficiencies where you can condense out some degrees of freedom to reduce the cost. Okay. So are there any questions on any of what we just discussed? Yeah.
Are there shape functions you would use for higher order?
Sure. You can embed this with trigonometric shape function. You can start out with a 2-node linear shape function. You can embed that with a cosine function or sine function, or there's actually an area within finite elements called generalized finite elements or extended finite elements. So those are different types of enrichments that people use. So yeah, if you have certain some idea of what the solution actually behaves like within the element, you can add that bubble shape function. Okay. All right. So let's take a look at a one-dimensional application, and with this we will pretty much finish the chapter on this one-dimensional finite elements, and from next time we'll start the two-dimensionals and three-dimensional finite elements. So we've been talking about all these linear two-node finite elements, right? And we've been talking about these simple one-dimensional problems. But what we have derived till now is also actually applicable to problems where the individual structural element actually behaves in a one-dimensional way. So one such example is this truss example. And if you try to look at any of these members, and if let's say for now we will restrict ourselves to small deformation. So what we are assuming is that each of the truss members is just going to either be under tension or compression. So it's a one-dimensional behavior of each of those truss elements. So in two dimensions, we know that all these connections are actually pins. So there's no moment transfer across this across these joints between the members. And in 3D, we have a ball and socket joint for a space truss. Another thing to point out here is the body force. So what do you think? If you have a real truss, is the body force on a real life truss 0? The body force is not 0 because there is some self-weight, right? But we say that we are going to neglect the self-weight of the truss in comparison to the loads that it is carrying. But so that is only an approximation because in reality, if we start to consider the self-weight of the truss, then this would become a bending member, right? Each of those members would start to bend and it would not be classifiable as a truss. So we make this approximation that the body force or the self-weight is going to be also approximated by nodal forces. So we're going to take half the weight of the bar of each element on this node and half on this node. So that's something that we normally do for trusses. So all right, let's see how we can apply what we have developed for a two-node finite element to all these different elements within the truss. Okay, so let's consider some element within a truss. Let's consider this element right here. And if this is 2D or 3D, that element could be oriented in some arbitrary three-dimensional direction. So we are going to say that this is our global basis, and the nodal coordinates of these two nodes, we are going to denote it in the global basis with x1, y1, z1, and x2, y2, z2. So these are the nodal coordinates. Once I know these nodal coordinates, then I know this direction E1, right? I can find out what this direction E1 is going to be if I know the nodal coordinates. And if you remember from our discussion for the one-dimensional finite elements, we developed the stiffness matrix in the direction E1 only. We said that our one-dimensional bar cannot move in the 2 and the 3 directions. So the degree of freedom that we were using was aligned along E1. So in 2D, as soon as you have E1, you can find E2 that is going to be perpendicular with the right-hand rule. But in 3D, there is a special case. So in 3D, which direction is your E2 and E3 going to be? Let's say this is the truss element. I know that my E1 is going to be pointing along this direction. But I could rotate this 2 and 3 in any arbitrary direction. So for three-dimensional trusses or space trusses, we actually have to specify some sort of an orientation of that element. And that orientation is just, you can just specify some E2, any E2 that is perpendicular. So let's say I choose this E2 as something that is perpendicular to that. And E3 will simply be obtained by the right-hand rule of cross product. Okay, so this is something that you will have to use if you are modeling a space truss in Abacus. And I'm going to assign some homework problem today that will require you to do a basic modeling of a space truss in Abacus. So you don't have to code this up. You can just use Abacus, and so we will try to start learning how to use Abacus now. Okay. So now with this, we found out that our element stiffness matrix was this. If we were all oriented along E1, this was the element stiffness matrix that we had before. So in order to extend this to 2 dimensions and 3 dimensions, all that we have to do is, let's consider the 2D, 2-dimensional case first. We are going to say that our degrees of freedom, and I think on the next page, so this is the local element axes, E1 and E2. These are the coordinate directions at, let's say, node 1, and the global coordinate directions were G1 and G2. So we know that we can relate the components of our displacement by using that transformation, coordinate transformation, right? So this is something that we talked about in the second or the third lecture in this course also. But this is not a very complicated thing. You can very simply verify that if somebody gives you a point or a location according to the global coordinates, so let's say these are the global coordinates of a point here, you can find out what are the element coordinates, that is the components in this coordinate system, by using this transformation. Okay, so cosine, sine, minus sine, cosine. This is a general 2-dimensional case. In general, for a 3-dimensional case, what you actually have is that instead of this 3 cross 3 matrix that is cosine, sine, and all that, this will be a rotation matrix. This will be an orthogonal rotation matrix, which we are going to denote with Q. And the property of these orthogonal matrices is that their inverse is actually equal to the transpose. So if you have an orthogonal matrix, you want to invert it, you'll see that that inverse of that matrix is the transpose. So knowing this, what you can do is you can express all your degrees of freedom that you had in the local, in the element coordinate system. You can transform those degrees of freedom to the global coordinate system. And the reason that we are trying to transform them to the global coordinate system is so that finally, if we assemble all our equations, we should be able to connect the degrees of freedom. The global degrees of freedom, if you mark them as x and y, then they can be assembled. But the local degrees of freedom, one element is pointing in this way, one element is pointing in this way, you cannot directly assemble them, right? So you have to transform the degrees of freedom from the element coordinates to the global coordinates, and then you can assemble them. So going back to this one, all we are doing here is, in 2 dimensions, we are using the exact same matrix. 1x element here, 2x element here, and this corresponding element is again 1x and 2x element. And all we are doing is adding zeros in the other two directions. Similarly, in 3D, we will have these 4, exactly the 2 cross 2 submatrix, and the rest of the entries are 0. So this is also something that is valid for other types of elements. Let's say you have a 2-dimensional element. So that has maybe a 4 cross 4 element stiffness matrix. You want to assemble a structure made out of two-dimensional elements. Then once again, you can just add a row of zeros corresponding to the 2-dimensional element, and then assemble all of them into 3 dimensions. So this is something standard procedure that you might actually have seen in structural analysis also. So once you do that, you will see that you can write out your element transformation matrix with a T. So now this case, this D element is actually the degrees of freedom at the two nodes. So for example, at node 1, we will have x, y, and z. So this right here is a 3 cross 1. This again is a 3 cross 1. So the total size of this vector is 6 cross 1. And all that vector denotes is the degrees of freedom at the two nodes. And this transformation matrix is nothing but the same rotation matrix right here and the same rotation matrix right here. And the off-diagonal terms are 0. So in this way, you can transform your element degrees of freedom to global degrees of freedom, and then you can assemble them back again. And the way to do that is this is the weak form for trusses. That in trusses, this is the exact same weak form that we had for one-dimensional problems, right? The only difference here is that we are going to calculate this quantity. We are going to calculate this quantity per element, and we are just going to add all of them together. So this would be a measure of the total strain energy stored for a small virtual displacement in that total in that global truss. Okay. So all I'm going to do now is to substitute this equation right here. If I substitute this equation into the formula for each element, what I will have is this d global transpose times this t transpose. So this is the t transpose, transformation matrix transpose, times the same element stiffness matrix right here, and dE, where dE is also t times d global. So this is t for the element times d global. And now all I'll do is I'll collect this term. I will collect this entire term and call that to be my global stiffness matrix. So what I have now is I can pull this d global out by assembling it, and what I'm left with inside is this entire matrix that goes right here, k global times this unknown vector, degrees of freedom in the global coordinates, minus nodal forces. There are no body forces in this. Okay, so because this is a truss, we say that we are going to get rid of all our body forces, and we are going to approximate any external loads and the body forces with the nodal loads. So now if you want to solve this, all you have to do is to make sure that this term is 0 and you have the same equation back. Okay, and the only thing new about this truss problem is that you calculate your element stiffness matrix, append it with the appropriate amount of zeros, and then transform it to the global coordinates and assemble it. That's all the difference between a one-dimensional problem and three-dimensional structures which have individual elements that act in a 1D way. Okay, so let's stop there and we'll meet on Wednesday.